Large language models, or LLMs, often struggle with slow response times when generating extensive text sequences. This latency stems from the inherent auto-regressive nature of these models, where each new token generated requires processing the entire preceding context. Such repetitive computation leads to a quadratic increase in cost with sequence length, making real-time, long context generation impractical. The transformer architecture, central to modern LLMs, employs a self-attention mechanism to understand relationships between tokens. This mechanism assigns 3 vectors to each token: query Q, key K, and value V. The query represents what a token is looking for, the key describes what it offers, and the value contains its actual content. When generating a new token, the model calculates its query vector. This query is then compared against the keys of all previous tokens to determine relevance. The resulting similarity scores, after scaling and softmax normalization, are used to create a weighted sum of the value vectors, producing the contextualized representation for the new token. Without an optimization like the KV cache, generating a sequence of n tokens means that for each new token, the keys and values for all n1 preceding tokens are recomputed. This redundant calculation is the primary bottleneck, causing the computational cost to scale quadratically with the sequence length. The KV cache, or key-value cache, addresses this by storing the key and value vectors for each token once they are computed. During subsequent decoding steps, instead of recomputing these vectors for previously processed tokens, the model simply retrieves them from the cache. This caching mechanism fundamentally transforms the computational complexity. The model only needs to compute the query, key, and value vectors for the token at each step. It then appends these new key and value vectors to the existing cache, making the generation process approximately linear with sequence length. The performance gains are substantial. Benchmarks have shown generation speedups of over 5 times, significantly reducing latency and improving throughput. This efficiency is critical for responsive conversational AI and enables models to handle long context windows and extended dialogues. However, the KV cache introduces its own challenge: memory consumption. The cache grows linearly with the sequence length and batch size. For large models and long contexts, the KV cache memory can rival or even exceed the model's weight memory, quickly exhausting GPU VRAM. For instance, a Llama 370B model with a 128K context window can require 42 GB of GPU memory just for the KV cache. This demand limits the number of concurrent users and necessitates sophisticated memory management strategies to prevent fragmentation and waste. To mitigate memory pressure, techniques like PagedAttention have become essential. PagedAttention, utilized by systems like VLLM, stores the KV cache in fixed-sized, non-contiguous blocks, allocated on demand. This approach significantly reduces memory fragmentation and waste, improving GPU utilization. Another crucial optimization is KV cache quantization, which stores key and value tensors at lower precision, such as FP8 or INT4, instead of FP16. This can reduce memory footprint by 50% to 75% with minimal impact on accuracy, enabling longer contexts and larger batch sizes. Advanced quantization methods, like NVIDIA's NVFP4 KV cache, can further reduce memory footprint by 50% compared to FP8, effectively doubling context length and batch size with less than 1% accuracy loss on benchmarks. This showcases continuous innovation in efficiency. Beyond single request optimization, prefix caching, also known as prompt caching, reuses KV states for common prefixes across multiple requests. For agent loops or multi-tenant SaaS environments, this can yield significant cost savings and improve time to first token. Dynamic KV cache management represents a newer class of algorithmic techniques. These methods adaptively allocate, compress, or evict cache entries based on token importance, attention scores, and redundancy analysis, optimizing for diverse resource constraints. In situations where GPU memory is severely constrained, KV cache offloading transfers inactive cache data from GPU memory to CPU RAM, or even SSD storage. This frees up high-bandwidth GPU memory for active requests, balancing speed with memory capacity. Emerging architectural approaches, such as DeepSeek's multi-head latent attention, compress the KV cache by storing a low-rank projection instead of full keys and values, achieving 7 to 14 times compression compared to standard multi-head attention. The continuous evolution of KV cache optimization, including hardware-aware quantization like FP8 on Hopper and Blackwell GPUs, and advanced memory management, allows LLMs to support context windows ranging from thousands to millions of tokens efficiently. Ultimately, the KV cache, combined with these sophisticated optimization techniques, transforms LLM inference from a quadratically expensive operation into a manageable memory bandwidth challenge. This enables the responsive, scalable AI experiences that define current and future large language models like ChatGPT.